Okay, thank you, Silvia, and let me thank all the organizers of this session, Variational Methods and Applications to Partial Differential Equations. I'm very happy to be here tonight and to share with you some free boundary problems in segregation problem. Okay, let me start. Sorry, I usually start with these motivations and these pictures, so I apologize for those who have already seen them. One class of problem which is important in this as a motivation are competition diffusion systems with lots of Volterra interactions. Just to simplify things, we have some densities UI which satisfy some reaction diffusion system with an interaction term that in this case is quadratic, is a quadratic polynomial in the UIs with some interspecific competition rates, Bij, which are symmetric in this picture, but appear with a minus sign in front. So they oppose both the growth and the spread of the population. And just to summarize, we have an evolutionary equation with some diffusion term, some reaction, and some competition. And we are interested in the case when the competition rates, Bij, go to infinity, to plus infinity. Okay, the UI here models the density of the ice population. Di are diffusion rates. Bij is the matrix of the interspecific competition rates, and the reaction term may be thought to be, for example, of logistic type. Actually, they will not play any role in what I'm going to discuss in this talk. A problem which is in fact related, even though it comes from completely different applications, are nonlinear Schrödinger equation systems of equations of interest in Bose-Einstein condensation in multiple spin states with a repulsive interaction potential. In that case, there is an energy which is minimized by our wave function psi I, and the energy has an internal part plus an interaction energy with Bij again positive numbers. In this case, the potential is quartic, so the interaction in the differential equation will be cubic. And one can consider the focusing or the focusing cases, depending on the sign of F, then it makes sense to fix the mass, the mass, and so. In that case, one sees that again, sorry, I didn't discuss the first picture. The first picture is a joint plot of the level set of the densities, U1, U2, U3, and because these competition rates are very large, there is one sees the creation of an interface, which are the blue lines here, and these blue lines, let's say the structure, the geometry of this interface will be the object of our discussion. Okay, so in this case, this is a picture of the moduli of the wave functions, a joint plot with 2 components, 3 components, and so on. Okay, in this talk, actually, we will consider only stationary cases. and we assume that all the diffusions are equal, just to start. So we can consider that the first system reduces to a system of this type, minus Laplacian of ui is equal to some reaction term plus the minus, the competition term, and we can think that the coefficients aij are fixed, and there is a large parameter beta in front of this. And our issues concern the asymptotics when beta goes to infinity, the possible common regularity properties shared by all solutions in a uniform way with respect to beta, the existence of segregated limiting profile, the regularity and the regularity of the common nodal set. Okay, well, let me give a definition of segregation in this context. We have a family of solutions, for I ranging from 1 to k. So we have a vector, and we, depending on this larger parameter beta, and we assume that there is convergence, at least in a point where it says, to some limit profile. And the limiting components are non-trivial, but have disjoint support. In general, in our application will be continuous functions. So if one of the components is non-zero, then all the others must be zero at a point. And we address question about the kind of convergence as beta goes to infinity, the regularity properties of the limiting profile, the geometry of the nodal set. And here is a partial list of the people who have contributed to this particular study of regularity of the limiting profile and geometry of the nodal set. And just to give, let's say, a picture of what can happen in one dimension, already the problem is significant, and we can imagine to have solutions are pair in this case, U1 and U2. We can imagine to have these solutions, for example, with some zero boundary condition. And when beta goes to infinity, what happens is that the limiting components U1 and U2, which are the limits respectively of U1 of the family U1 beta and U2 beta up to subsequences, they segregate, okay, according to the previous definition. In the one-dimensional case, the interface for this model is just one or a finite set of points, while in 2 dimensions, true field boundaries arise, and the geometric structure is an interesting object of investigation. Okay, so let's fix our mind. We can consider a number of possible models. The first one we introduced is what I call the Lotka-Volterra system, and has quadratic interactions. You see, this is a quadratic polynomial in the UI with symmetric competition rays. Okay, and then one can consider the Euler-Lagrange equation associated with this Gross-Pitayevsky energy, and in that case, actually, one sees that the competition term is not quadratic anymore; it is cubic, and again, it has a variational structure when the matrix Aij is symmetric and has not in the opposite case. The same happens. Okay. Also, for the Lotka-Volterra interaction, one can consider non-symmetric interactions, and in general, one can play with a class of possible models. One can change the standard diffusion with fractionary diffusion, considers polynomial or power interactions, which may have or not a variational structure depending on the symmetry of the matrix of the competition of interspecific competition rates, and depending on also on the choice of the exponent pi. And then, and I will actually focus on this last problem. One can consider a case where this competition doesn't hold, doesn't have an effect in the same point, but has some range of effect. So the interaction, the competition takes place at a distance. For example, a shooting distance, just to say. And again, this class of problem may have a variational structure in some particular case. Okay. And the last problem I will discuss tonight is the case where the diffusion operators are local ones, but they are different. So each population diffuses with a different matrix, and this constant matrix. So there is some anisotropy, some different behavior with respect to different directions. Of course, one could elaborate more, but these two last cases will be of our interest in this talk. So what question can we address when looking at this big class of problems is what does the particular expression of the interaction matter? So can we understand from the limiting profiles whether the interaction was quadratic or cubic? We can address the question whether, at least in the limit, there are variational principle holding. What are the rules of diffusion, and what is the effect of the diffusion rules on the problem? Sorry, and what is the role of distance? Okay, let me just recall some interesting features of the pointwise interaction with equal diffusions. One thing that one possible entrance point to this problem is to consider already to define a functional, which is in this case the sum of the Lagrangian functionals and the Lagrangian energies associated with each single equation, and minimize this functional. Why it is called J infinity will be clear in a moment, among a class of segregated states subject to some boundary and positivity condition. And something that can be proved is that this minimization problem with some mild reasonable assumptions on the capital F have a unique, this is non-trivial, segregated stationary configuration, which is Lipschitz in the sense that all components are Lipschitz functions. And if we consider the nodal set, that means the set where all components are zero, simultaneously zero. Sorry, the nodal set is the set where all components are zero. This has a nice structure. There is a singular part, which is small in dimension, and a regular part, which is a collection of hypersurfaces of class C1 alpha. And it is important to remark that Okay, here I am talking about stationary configuration and not minimizers, because one can give also a definition, the proper definition of stationary configuration. And the stationarity condition implies that at the regular part of the boundary, so when you pick a point in this regular part, there are only two components which are non-zero in a neighborhood, and these two components have the property that at this interface their gradients are equal and opposite. And in 2 dimensions we have even more, because the singular set is a locally finite number of set of points, and the regular curves of the interface meet with equal angles at such singular points. Okay, what is interesting of this result is that can be stated the following way. Let me recall that if you take one scalar solution of a stationary Schrödinger equation for a reasonable potential, for example, in L infinity, and you take the nodal set of such solution, then the nodal set has exactly the same structure as I described before. So there is a possible singular part. Singular here means that the gradient is 0, which is small in dimension, and a regular part, which is clearly regular at this point, because it's regular in the sense of the implicit function theorem, which are of class C1 alpha. Okay, so what happens is that our segregated minimizers, as far as their nodal set is concerned, share exactly the same geometric properties of the nodal set of real valued solutions of Schrödinger equation. Well, okay, now why I was calling this functional J infinity, because in fact it can be seen as the limit of a singular perturbation, singularly perturbed class of functional, where there is a penalization term, which is this one, and in this, if you put a large scalar beta in front of this part, then this has the effect of forcing segregation in the limit. And when beta goes to infinity, we can look at the limiting profiles and at the limit, minimization of the limiting function. And then you see that we can state some theorem, which is important. Now I have just neglected the internal forces F of UI. They could be there, but they play no role, so I will just avoid to write them. And then what we can prove is that if you have a family of solutions of this problem and you let beta go to infinity, then there are uniform bounds in spaces of Holder continuous functions, and in fact these uniform bounds entail the existence of limits up to subsequences and of limiting profiles. And then not only we can look at the limiting profile of the families of solutions, of any type of solution, which have an initial bound in H1, well, the limiting profiles have exactly the a nodal set sharing the very same properties as the minimizers of the energy. And something which is maybe of some interest is that the basic rules of for segregation do not depend on the particular form of the interaction. This means that if I take the last theorem and instead of having a power 2 here, I have just a power 1, then I have the very same theorem and with the same structure of the nodal set. Okay, now let's go to the interaction at a distance, and then let's look at the variational problem. So we have a functional which is already defined on segregated states, but now segregation has a stronger meaning, in the sense that not only supports are disjoint, but the supports of the different components must have a distance at least 1, or at least whatever. Okay, here now again, for the sake of simplicity, we consider an energy which is only the gradient, the square of the gradient integrated. Okay, so if we think of having 2 components, we have one component here, the blue one, which is say positive on this upper region, and then we have a green component down here with its support. The 2 supports must be at a distance which is at least 1. We consider the positivity sets of SI, and these have distance exactly 1. Of course, when we have more than 2 components, the situation becomes more complex. But in any case, the distance between the positivity sets must be always at least 1. And then we have this theorem. If we consider a minimizer of this functional in the space in the constraint space, and if we denote by SI the positivity sets of the components SI, then the components SI are subharmonic in omega. And they are harmonic in SI, whatever this means in the interior of SI. That in principle could be even empty. The positivity sets mainly by definition satisfy an exterior, a uniform exterior sphere condition in an appropriate sense, and this has a nice consequence, because each component, thanks to this exterior sphere condition uniform, is Lipschitz continuous, so they are in fact continuous functions. And SI, the positivity sets are open. This is somehow obvious. And then there are 2 less trivial facts. The Lebesgue measure, the n-dimensional Lebesgue measure of the free boundary is 0, and its house of dimension is strictly smaller than n. Be careful, we could imagine less or equal than n minus 1, but at this moment we can just say that it's not the full house of dimension. And the supports, the positivity sets, have a distance exactly 1. Okay, so this picture, where here we have a distance exactly 1, is allowed, while this picture is not allowed, because here there are in fact points where the distance between the supports is strictly larger than 1. Okay, now let's go to let's have a closer look at the geometry of this these interfaces. Okay, and in fact, here it is plenty of open questions. We actually don't have such a nice result as for the pointless interaction. We don't have, let's say, we would love to have to extend to say that there is a regular part and a singular part, and that the singular part is somehow residual in some appropriate sense. What we can actually do is to assume some regularity at the interface, and we assume that the boundary of the positivity states are regular enough. They have curvatures, they are C2, and we also assume that these curvatures are smaller than or equal to 1. Okay. We agree that to take a positive direction, the outward normal. Okay. And we suppose not only that the curvatures are smaller than 1, but they are bounded away from 1. So they are all less or equal than 1 minus delta, at least in a portion of their boundary. Okay. And in this case, we have that they are these two. There are only two components interacting, and one of these boundary, the boundary of the positivity set of one component is a graph over that of the other component, that they are both graphs on the tangent at some point. And so, and not only, but to each point of the boundary of, let's say, Si, there corresponds a unique point of the boundary of Sj. And of course, at a distance exactly 1. And so if you look at the radius of curvature, at two corresponding points, y0 and x0, then of course the radius, the second radius is 1 plus the first radius. Okay, and this fact entails some relations among the principal curvature at corresponding points, which can be written this way. This is somehow elementary. In the case the curvature, one of the curvatures tends to 0, also the other tends to 0, and the ratio. Sorry, I'm back. Can you hear me?
Yes, Susanna.
Yes.
Oh, sorry. Okay. Sorry. So okay. So we in case the curvature become equal to 1, then you can lose regularity, and that can be cut. We don't allow so, and so we. This is this assumption. This is an assumption that we are doing, that we are making on our free boundary. In such a case, we were able to prove with Tavares, with Soave, Tavares, and Zilio, to find what are the extremality conditions. Please remember that in the case of pointwise interaction, the extremally condition was the equality of the normal derivatives at regular points of the free boundary. In this case, the ratio between the boundary conditions of the components is not constant, is not equal to 1, but it is equals the geometric, the ratio of the geometric averages of the curvature at the two corresponding points, and in case some of the principal curvature annihilates at a point, then they would annihilate also at the other point, and this ratio will tend to 1. Something which may be interesting to be pointed out is that in that case there was a previous study by Caffarelli, Patrizia, and Título regarding the quadratic interaction, the quadratic interaction with long range, and they found a similar extremality condition, but you see, with here before we had the square. So what happens is that if you don't put a distance, the boundary conditions, the extremality conditions at the nodal set, that in the pointwise competition case does not distinguish between cubic and quadratic interactions, while if you put a distance, even a small distance, you can see a difference. Now, I'm sorry, my time is over technically. Maybe I will. Okay, so let me just finish this talk by saying, okay, there are connected problems. You can consider either the sum of the Dirichlet energies or the, for example, the problem, the eigenvalue problem associated. And then you can consider insert a parameter in your analysis, so consider the distance between the supports as a parameter, and look what happens when R goes to 0. And then, for example, there is a nice result by Soares, Tavares, and Zilio about uniform Lipschitz estimates of this minimizer when R goes to 0. Okay, sorry, I have lost some time, and I cannot introduce the next problem, which is the one with the different different isotropies in the diffusions, which is also a very interesting and intriguing problem. There are many open problems in this area, and I would like to encourage people to have some to try to elaborate on this. So thank you very much for your attention, and sorry that some technical problems have slowed my talk, but this happens with this online talks, and I hope we will be able to meet in person all together very soon. So thank you very much for your attention.